Our next talk is on the composability in watermarking schemes by Jiahui Liu and Mark Zandri, and Jiahui is giving the presentation. So no, the presenter is Sachi Moneta.
Okay, hi everyone, I'm Sachi, and I'm going to be talking about composition and watermarking schemes. Yeah, this work is by Jiahui Liu and Mark Zandri, and they couldn't be here today, so I'm filling in for them. So I'll start by describing what watermarking is. Watermarking is an old idea, and it basically says that if you have an object, you can embed a mark in it, and any attempt to remove the mark would destroy the object. So in the software regime, you can think of having a piece of code, and you embed some mark in it, and if the mark is removed, then the program is destroyed, and it's not usable anymore. And we can also think of watermarking cryptographic functionalities. So a watermark cryptographic functionality would have the regular evaluation key generation algorithm that the plain cryptographic functionality does. But in addition to that, it has two extra algorithms. The first one is a marking algorithm, and this algorithm takes in some circuit and a mark M, and it outputs a marked circuit C prime. This would have the mark embedded in it. And then we have an extract algorithm, which takes in the marked circuit C prime and either extracts the mark M or it outputs bot. And we require two additional, in addition to the correctness and security of the plain cryptographic functionality, we have two additional properties. The first one is we call functionality preserving. So on input a circuit C, the mark algorithm should output a circuit C prime, which preserves the original circuit's functionality. So this just means that on most inputs X, Cx should equal C prime X. And then the next condition that must be satisfied is unremovability. So given a program C prime, no efficient adversary should be able to come up with the program C star such that C star preserves C prime's functionality on almost all inputs, and also but does not preserve the mark. So when you run extract on C star, you don't get M. So in other words, if there exists a C star that preserves C prime's functionality on almost all inputs, then extract C star must output M. And there's been prior work on watermarking cryptographic functionalities, such as pseudorandom functions, secret key encryption, public key encryption, etc. But one of the downfalls of these the constructions of these watermarked functionalities is that they're very ad hoc. So every cryptographic functionality has a separate construction to make it watermarkable, and then a separate from scratch security proof. So this is counterintuitive to what we do in cryptography. Well, what we want to do in cryptography is take building blocks and build advanced functionalities from these building blocks. So we can ask the following question. Let's say we have building blocks P1 through Pk, and we build an enhanced functionality P from these building blocks. Then if we have watermarkable versions of these building blocks, can we compose them in some way to get a watermarkable version of an enhanced functionality? So the main question this work asks is, can we compose building block watermarkable cryptographic functions to obtain more advanced watermarkable functions? As a concrete example, we know that pseudorandom functions and a MAC scheme gives us CCA secure secret key encryption. So if we have a watermarkable pseudorandom function and a watermarkable MAC, is there a way to compose these to obtain watermarkable CCA secure secret key encryption? And this work resolves this in the affirmative. So in particular, they show a composition theorem for watermarking. So if a black box cryptographic construction of a target primitive P from building blocks P1, P2 through Pk, if they satisfy some mild conditions, then if we have watermarkable versions of these building blocks, we can obtain a watermarkable version of the enhanced functionality as well. So some applications of the main theorem. So this is a list of building blocks, and that imply, so PRFs and MACs in the plane model, like I said, imply CCA, secure secret key encryption. So this theorem implies that if it's enough to build a watermarkable PRF and a watermarkable MAC in order to get a construction of a watermarkable CCA, secure secret key encryption, and we don't need to come up with a ad hoc construction for these buildable primitives. And the primitives with a star, they don't need to be watermarkable, so the result is even stronger in the sense that we can combine plain versions of building block primitives with watermarkable versions of other building blocks to get a watermarkable version of the enhanced primitive, and I can go over it in a bit more detail towards the end for what the condition is for the building block to be plain. So along the way, along achieving this composition theorem for watermarking, this work also strengthens the security definitions or the unremovability definition that we have from watermarking. So recall that the unremovability definition said that no efficient adversary should be able to come up with a circuit C star that preserves C prime's functionality but does not extract the mark M. They strengthen this property by saying that even if a program C star is not exactly functionally equivalent to C prime, but just has the guarantee that it wins the security game of the underlying primitive, even then it must extract the mark M. So this is a stronger definition. So as a concrete example, if the functionality we're working with is CPA, secure secret key encryption, then no adversary should be able to come up with a circuit C star, which wins the CPA security game, but does not output the mark when we run extract on it. So how do they, so now I'm going to go into the construction. So let's say we have a plain building block primitives, P1 through PK, and we have a black box construction of the plain target primitive P. Then if we assume that we have watermarkable versions of the building block primitives P1 through PK, then the construction of watermarkable P closely resembles the construction of plain P from P1 through PK. That's all I'll say on the construction. But now let's assume that we have a watermarked P from these watermarked building blocks P1 through PK. Then the mark, so if we want to mark this watermarked program P with mark M, then we mark M on each of the building block primitives P1 through PK. This would give us marked building block primitives P1 prime through PK prime, and then we put these marked primitives through our construction to get the marked target primitive P prime. And if we want to extract a mark from P prime, then we run the extract algorithm on each of the building block primitives P1 prime through PK prime and output the mark that each of these building block primitives should have outputted. And note that if a program is honestly marked, then because we're marking the same mark M on each of the building blocks, when we run the extract algorithm on our target functionality, each of the building block functionality should output the same mark M. So now, that was, okay. So now going to the unremovability security intuition. So we want to say that if there exists a circuit C star which wins the security game for our target functionality P, then it must extract a mark M. And the intuition for this is a reduction to the unremovability security of one of the underlying building blocks. So in other words, the intuition is that if an adversary wants to remove a mark from the watermark target functionality P prime, then it must remove all marks from each of the underlying building block watermark functionalities, P1 prime through PK prime. And this would and then the reduction says that you can turn any adversary for a program C star for P prime into an adversary for one of the building block functionalities, P1 through PK. And that would be a contradiction because that would break the unremovability property of the building block watermark primitives. Yeah, and in the case, so if recall in this table here, we had, there's composition theorems where not all the building blocks need to be watermarkable. So the reduction would either break the unremovability of one of the watermarked building blocks, or it would break the plain security game of one of the building blocks that's not supposed to be watermarked. So in either case, there will be some type of contradiction that this reduction would achieve. Okay, but to make the above reduction go through, the security game from plain, so recall that plain P has a construction from building blocks P1 through PK, like unwatermarked building blocks. And in order for this reduction in the watermark setting to go through, the plain security reduction from P to P1 through PK, it must satisfy some minor constraints. And they call this watermarkable compatible reductions in their work. The definition is quite technical, so I won't go into it. But turns out that the constraints that they put, like a lot of existing reductions in the plain in the unwatermarked setting, they already satisfy that. So the theorem still has a lot of applications. And now I try to go into why all building blocks, or why all building blocks don't have to be watermarkable. So if you have a construction from building blocks P1 through PK of an enhanced functionality P, then only the building blocks whose keys are used in the main key evaluation algorithm of P, only those building blocks need to be watermarked. And all the functions with keys that are generated online in P's evaluation algorithm and are only used in the security game, they don't need to be watermarked. So that's the condition. So for example, when you build CCA secure public key encryption, you need one of the building blocks is NISC, and you don't need to watermark this. So yeah, that's you see the paper for more details. Thank you.
Thanks for the talk. Any questions? I hope you can answer them, though you're not the author.
You said you gave a strengthened security definition of watermarking. Do existing constructions of watermark primitives meet your strengthened security definition? Or I mean, they're.
I think, okay, so I'm not sure, but I don't think prior work meets the security definition. I think prior work talks about just functionality preserving, but I think this is a caveat of the composition of watermarking. Like the theorem that they achieve along the way also comes up with this new security definition. So this only holds for the composition, I think. Yeah.
Okay, thank you.
Yeah.
So in the definition of removability, you only require that you cannot remove the watermark if the circuit agrees with the original circuit on most inputs. But so
that's the original unremovability, yeah. But their unremovability says as long as it wins the security game, you must extract a mark. So it doesn't have to agree on almost all inputs. Even if it just wins the security game, it must extract a mark.
Okay. If there's no more questions, then let's thank the speaker again and